Okay, so the idea, right, is that again we form carbocations and they're not stable. So anything we can do to um, rearrange our carbocation to minimize that, um, it's going to happen, right? It's just going to lower the energy of the system. And so that's really the whole goal of this. So here we can't do any rearrangement in the middle one because there's not a pi bond nearby. They're all secondary carbons. None of them have a pi bond. But in our first one, what do you guys think is going to happen?
Is it gonna be like the same thing as the other one?
So what's going to happen here, and this is going to be very unique, is that in the course of this reaction, um, we want to see this type of shift, right? But when we think about our rings, what type of rings are most stable?
The 6 carbon ring.
Yep. So a cyclohexane is always going to be our most stable um, molecule. But in this case, we can't really do anything. But what's going to happen in this one that happened in our third one?
The methyl shift.
Yep. We're just going to have that methyl shift again. So this is going to come here like that. And so then we are just going to make this like this. So now our plus charge is going to be there. Does that make sense? Again, we have a secondary carbon adjacent to a quaternary, right? Whenever we have a secondary adjacent to a quaternary, we have a methyl shift. Matthew's talking to other people. Too good for this chat. It's okay. What if he's talking to us? We can't hear him.
Yeah, I was gonna say that.
That's okay. All right, so that's it for those. So that's something to keep an eye on is that whenever you're doing those ring expansions or other stuff, not ring expansions, methyl shifts and whatnot, just if you have a secondary carbocation, see if you have a quaternary carbon nearby or you have a pi bond nearby or something like that. But this is going to be those first, the outer third ones are going to be our most stable one. All right. Identify the electrophile and nucleophile in the following reactions. All right, explicitly. So when we do reactions, how can you tell if something is a nucleophile or an electrophile? Do you have any idea?
I have read about this.
If it has like lone pairs and electrons.
That is a key dead giveaway, but it's going to be what actually does the attacking. Whatever starts the arrow pushing, that is going to be our nucleophile, right? So in our first one, there's something that's a dead giveaway that should tell you it's a nucleophile. Do you know what it is? It's the metal. Anytime you see lithium attached to a carbon, like lithium, like methyl lithium, lithium ring, or something like that, sodium or anything like that, anytime you see a metal attached to a carbon compound, what is actually there is that we have lithium. What we see drawn is that usually you will see lithium drawn to a CH3 methyl like this, right? That's what that Me is, correct? But in reality, this is an Li plus, it's a cation, and then we have a CH3 with a lone pair minus. So the lithium is acting as a countercharge to the CH3 minus, right? It's balancing it out. So you can think about this as kind of like an ionic bond type of thing. And so anytime you see a metal and a carbon compound like that, this is your nucleophile. Always, always, always. Okay? So Melissa, any idea on how you identify the electrophile?
Would it just be the oxygen?
It's not the oxygen. It's what's attacked. So what is my nucleophile? The methyl or the lithium? What am I adding to that molecule?
Oh, the methyl.
Okay, so the methyl is my nucleophile. Where the methyl adds, that carbon is my electrophile. So what is my electrophile on this?
The lithium.
No.
No, the methyl.
No, the methyl is my nucleophile. We just said that. What's the electrophile?
I don't know.
It's where it attacks. So where is the methyl attacking?
Oh, the carbon that's bonded to the oxygen?
Yep, that is my electrophile.
Okay.
So whatever does the attacking is the nucleophile. Whatever is attacked is the electrophile. All right? Does that make sense?
Yes.
So now take a look at the bottom one. Try to identify it on your own. I'll give you guys 30 seconds. Try to identify the nucleophile and the electrophile on your own. And I will sit here and stare out the side of my room quietly. Oh, it got cold. It was so nice today. It was like 65 here yesterday. Now it's in the 40s. It'll never be warm again. Okay, so who wants to identify the electrophile? Who wants to identify the nucleophile?
I think I'll do the nucleophile, if that's okay.
Okay, so Matthew, what is my nucleophile?
I'm going to say the CL on the.
Nope. Beep, beep.
Okay.
So what is actually attacking? What is adding?
The
The
oxygen.
methyl.
The oxygen.
Oh.
This whole thing, the HOME, right? The OME is what's adding, but it's the oxygen itself, right? That is what's actually adding. That is my nucleophile. Does that make sense? Because this here, right, is adding onto there. So Melissa, what is my electrophile?
The Cl.
Nope. Because am I adding to that Cl? Am I attaching it? Am I attaching to it?
Well, no, that's where we have
No. Where is my OME attaching to?
the carbon.
That's it. That is my electrophile.
Okay.
What is the chlorine? It is not the nucleophile. It is not the electrophile, but it is something else. 2-word phrase. Give me an L. Give me an E. Give me an A. Give me a V. Give me an I. Give me an N. Give me a G. GROUP. Leaving group. Is this here in my product?
No.
So that means it broke out. It left, right? If it's not there in your product, it is a leaving group. That should be a dead giveaway. So write that down. If it is not there in your product, it is a leaving group. Nucleophile, it is what is adding to my molecule. Electrophile is the site where the thing is adding, right? Does that make sense?
Yeah, the only question that I have is that I mean, you said that like the methyl group is not like part of the nucleophile, but
it is part of the nucleophile. It's the oxygen that's attacking, but the whole thing, the OME is the nucleophile.
Okay.
So what I'm trying to restate what I just said, the OME is my nucleophile because that's what's adding, right? But the actual site of nucleophilic attack, like what's actually doing the attacking, is the oxygen.
Okay.
But the whole OME is my nucleophile, right? This whole thing here can be considered my electrophile, but this is the site of the actual electrophilic activity. That's where I'm adding things. So always ask yourself, what's adding and where is it adding to? What's adding? Nucleophile. Where is it adding to? Electrophile. And if it's not there in your product, it probably was a
leaving group.
Leaving group. How are you guys with that? Matt, how are you doing with that? Matthew?
I see it now. I understand.
Okay.
I think that yeah.
Don't worry about it. This takes a while, so this is a new concept. So
one quick question though.
No.
The O and the OH right here. Where does the H go?
So this is going to be a whole mechanism thing. Basically, what's going to happen is that this H is like this. And so what ends up happening is that in the course of this reaction, this is going to attack here, right? This will rearrange and this is going to pop off. It's a complicated couple of steps. Not complicated, it's just 2 steps. And so then you're going to have this as your intermediate, like this, where you have the O and E and you still have the hydrogen. And why it does that, I don't know. I need to clean my screen. I clean my screen in still, but this happens, right? So what's going to happen is that this chlorine that got popped off is just going to come back and take that off like that. And then it'll make it back to neutral. These are complicated steps. This is something you don't worry about for now. What she's trying to get you to do is to identify what are nucleophiles and electrophiles so that when the time comes, you will know where your arrows need to start from. So for those of you viewers at home, we're going to say a box is a nucleophile. And we are going to say a circle is an electrophile. So our nucleophile is going to be, in these cases, both of these here, right? Our nucleophile are going to be these species here. Okay, does that make sense? It's what is adding to it, right? So what do you notice about the same electrophile both times? What is a common theme of that electrophilic site in both of these?
They're both carbons.
Carbons, go on. Be more specific. What are they connected to?
Oh, double bonded to an oxygen.
So what you find is carbons double bonded to oxygens can be really good electrophiles. So this is something you guys should start keeping an eye on, is that you will learn some things are better at electrophiles than other things, right? So do you guys know what an electrophile and a nucleophile are? Nucleophiles are electron rich. They have very strong negative charge. What's in the nucleus? What subatomic particles in the nucleus?
Protons and
Protons and neutrons, but what charge do protons have?
positive.
Positive, right? So nucleophiles, strong and negative charges, they are attracted to places with a lot of proton density because positive negatives attract, right? Electrophiles typically have low electron density, so they have more, things happening with the nucleus, and so since they have protons, a lot of positively charged, they are attracted to electrons. They are electrophiles, right? So for those of you who don't know, word, like basically word structure and stuff like that, phile means to love, right? So like if you were an Anglophile, you would love the English. If you're an electrophile, you love electrons. Does that make sense? That word, that root word typically has a much darker connotation in English, but in this case, if you think about it, so the electrophiles love electrons, nucleophiles love nuclei or positively charged areas. Okay, so what we find is that these carbonyl carbons are really good electrophiles because they don't have a lot of electron density. It's going towards the oxygen, but we will go through that. But the idea is just recognize where your electrophile and nucleophilic and electrophilic things are. All right. Let's go continue. Using table 6.1, estimate the enthalpy change of the following reaction under standard conditions. So how do we calculate enthalpy change?
Reactant products minus reactants.
Well, it depends. If we're doing bond to enthalpy, we do reactants minus products. So do you have table 6.1 at the end of this thing? Yeah.
Okay, yeah.
So if you have bond associations, it's reactants minus products. Reactants minus products. If it was like the energy of the molecules, like delta H of formation, then it's products minus reactants. But if it's bond enthalpies, you just do that, right? So bonds of the reactants minus bond energies of the products. Make sense? So you would just go through, and what's the one thing you have to be careful of in this entire problem? I mean, they should cancel out, but what's the one thing that people are probably going to forget? Your carbon-hydrogen bonds. They should cancel out, so you don't have to worry about them. But if you're ever doing a problem like this, don't forget that they're there, right? In reality, you only need to take care of the bonds you're breaking, right? Minus the bonds you're forming. So which bonds are you breaking here?
The fluorine.
Carbon to fluorine, right? Because that's not in there. And then an oxygen to hydrogen, because that's not there, right? So then what bonds are you forming here?
A carbon to an OH. And
A carbon to an oxygen, right? And then hydrogen to fluorine.
Yeah.
So when you do these, you don't have to worry about the other bonds that are not breaking because they should cancel out. Does that make sense?
Yes.
All right.
And then
Question.
you suppose reactants minus
products. Yep. So bonds broken minus bonds formed is probably the easiest way to think about this. So it would be bonds broken minus bonds formed. And so I know if someone sees this, they're going to be like, wait, what about these other bonds that are all there? Well, even if you add those in there, they're still all here. So they're just going to subtract, right? You don't have to worry about those ones because they're just going to cancel out. Because they're still, so bonds broken minus bonds formed is going to equal your delta H. Tasty enthalpy. See, this is something teaching in Gen Chem, I teach you the long way, but in organic, I show you the short way. You're probably like, we could have used that information out. All right, so answer each of the following questions. Does a reaction with a positive delta S and a negative delta H favor reactants or products? So what is that? What do you guys know about that?
positive S and negative. What do you think about this?
I'm gonna say reactants.
Okay, so in order to have this, right, the idea here is that our general idea is that in order for a reaction to favor products and other stuff, right, we got to think about what our delta G is, correct? So when we think about this one, so if we have a delta S that is greater than 0 and a delta H that is less than -0, it should favor the products. So if you have a positive delta G, you should favor reactants. For your KEQ values, when it's greater than 1, it favors the products. When it's less than 1, it favors the reactants. If it's at 1, it's at equilibrium. So any idea on this last one?
I think it would be products.
Yep. So if it's at higher temperature, it should favor your products here. So if you're, this is one thing I'm always a little like, like what am I thinking of? Is that when you have delta S, and so if you have positive delta H and positive delta S, you fall into what I like to call the I'm not sure category. All right. So if you have positive delta S and positive delta H, it is going to favor the products if you have a high temperature. I don't remember if this falls into the high temperature. Did she tell you what a high temperature is for this?
I don't think so, but now that I think about it, isn't 298 kind of like the standard that we use?
It's room temperature. So it's like 25 degrees Celsius. So like 60 some odd degrees Fahrenheit.
Would that be this 25 degrees Celsius room temperature?
About, yeah.
Okay, so it is under normal temperature then, because there would be a Kelvin for it.
So then it won't be spontaneous unless you have a high temperature. So that's why you should ask her about this question. Or do you have your answer key that you can double check real quick?
Yeah.
Okay, I'm gonna pause this real quick recording. So what does delta G equal? Matthew, do you remember what delta G equals?
Was it I don't remember actually.
So delta G formula, right, is just, I would say try to remember this one if you remember it. If you remember anything, it's delta H minus T delta S. So this is the important thing here. This is why I was saying it depends on the temperature, right? So when delta G is negative, it will always favor the products, right?
Yeah.
So if delta H is negative, delta S is positive, that means it'll always favor the products. When they are but when they're both positive, that's when you've got to check what the temperature is. So if I plug this in, it would be 14 minus 150 times 298, like that.
Wouldn't it be like 0.15 because you have to divide it by 1,000?
No, because, oh yeah, this is, sorry, this is going to be, we can just change this to 14,000. Sorry, I didn't see that was kilojoules. I tell my kids all the time, pay attention. Right, so we can just convert that. So this one is going to be 14,000 minus, and then 150 times 298 equals 44,700. And so when I do that math, I get negative 30,700 joules, or negative 30.7 kilojoules. Right, so what this means is that if you ever do this calculation and delta G is negative, it is always going to favor the products. Make sense? Matthew, you look a little unsure.
Oh no, I understand.
Okay.
Yeah.
Any questions? Are you guys good?
I get it, but I'm just confused because we didn't get the same answer as her.
What did she get?
She got negative 74,000 joules per mole. Oh, but average is in kilojoules, but it should still be the same. Like
You said negative 74,000?
Yeah. And I tried like adding them instead of subtracting them because I thought maybe that's a mistake that she did. But
it might just be a weird calculation problem. So I would say just ask her about it. That's not to say that I didn't make a mistake either, because that was just, I will double check, but I'm pretty sure that's what delta G is. I'm just gonna, delta G equals delta H minus T times delta S. So we have our delta H, we have that. So even if I did the conversion, I'm not sure, but it still favors the product. It still favors the products, right? So that's how you just calculate. I would say double check with her. Again, always go with your professor's answers, right? So you don't want to go with mine, because I know what I'm doing, but at the same time, she's your professor, right? So if I'm making a mistake, you want to make sure that you double check with her. But all right. Circle the best answer for the following 5 multiple choice questions. What is the index of hydrogen deficiency, also called degrees of unsaturation, for a compound with the empirical formula? So you guys remember this formula for calculating it?
Yeah.
So we simply say 2 times the number of carbons plus 2 minus the number of hydrogens minus the number of halogens minus the number of nitrogens. So all divided by 2. 2 times 9 is 18 plus 2 is 20. 20 minus 16 equals 4 over 2, which means we have a degree of unsaturation of 2. Make sense? All right. So that's an easy one. Make sure you have that formula memorized, because it's going to come back constantly. What is the relationship between the 2 compounds? The same compound, enantiomers, diastereomers, or meso compounds? Are they mirror images of each other?
No.
All right, so this rules out enantiomers if they are not mirror images of each other. Also, are they the same compound?
No.
Nope, I can't rotate them. So now they lose diastereomers and meso compounds. If they are meso compounds, what do they need to have? What needs to be present in both molecules?
The symmetry.
Yep. Do I have symmetry in either one?
No.
Nope. So that rules out meso compounds. So just by going through those basic questions, it's a diastereomer. And what is a diastereomer, Matthew? I know you know what diastereomers are.
It's the one where
kind of cut out for me. I don't know if you cut out for Melissa as well.
The one where it's like three-dimensionally different, which is
It's basically, this is basically when you have stereocenters, right? How many stereogenic carbons do I have? How many stereocenters do I have?
2.
You have 2, right? So say, for example, I'm not saying that this is what the stereocenters are, but say you have your stereocenters were RR. What would the enantiomer be of this?
SS.
It would be SS, right? So this would be an enantiomeric relationship. If I change just one stereocenter, this is what's called a diastereomer. You need 2 stereocenters. So if I just change the second one, or if I change just the first one, those are diastereomers. So all of the outside arrows, all of those relationships between those are all of those are diastereomers to each other. The 2 going across the middle are enantiomers because I'm flipping both at the same time. Does that make sense? So an enantiomer is when you change all of the stereocenters. So if you had all R, if they all become all S, or if you had like RS, RS, and they flip to SR, SR, right? When you flip all of them at once to the other thing, that's when you have enantiomers. When you only change one, or if you don't change all the stereocenters, then that's when you have diastereomers. Does that make sense? And so in order to have a diastereomer, you need to have at least 2 carbon centers, 2 stereocenters. If you don't, you won't have a diastereomer. Okay. Next up, predict the sign of delta S for the following reaction. Any idea? So what do you guys know about, what's delta S?
I forgot what it meant. Like I know that like what it means like in an equation, but I forgot like the meaning of it.
It's entropy.
Yeah.
So how would entropy increase? There's 2 things that are dead giveaways when you have an increase in entropy. If you form a gas, that is a huge increase in entropy. Also, if you go from 1 to multiple, if you break anything down into more parts, because entropy refers to like degrees of freedom. So 2 things are going to have more freedom than 1 thing. So anytime you do a decomposition like this, this should be positive. Does that make sense? So if you form a gas in a reaction, that should increase entropy. It's going to be positive. If you go from a lot of things to 1 thing, then you'll have a negative entropy. Does that make sense?
Yes.
You guys don't seem like you're really happy with this answer.
I mean, it makes sense. Like, I think that like I've kind of just forgot about this stuff in a way.
That's fine. All right. Next up, what is our least stable carbocation? Think back to when we were doing our carbocation rearrangements. Why were we rearranging them? We're trying to make them more stable, right?
Yeah.
So what can we do here to make these more stable? Or not, sorry, we're not doing a rearrangement now. What were we trying to get? What were we trying to form to be our most stable carbocation?
We were trying to add a
tertiary, right? Tertiary was our more stable one. So what should be our least stable one? Methyl, right? The more carbons we have around that, you guys need to put that together. Is less stable than a primary, is less stable than a secondary, is less stable than a tertiary. These carbon groups that are attached to my carbocation help stabilize it. So the more substituted the carbon is, the more stable it is. If you have resonance nearby, the more stable it is. All right. So this is a very important order you need to memorize now. Write it down, Matthew. I don't see you writing. You need to write this down. This is something that is going to come back to haunt you throughout the rest of chemistry, because when we start doing reactions, when you start doing something called SN substitution and elimination reactions, This is going to be one of the fundamental concepts. And you need to know that when you have carbocations, the more carbons that are attached to that carbon, the more stable it is. The less carbons that are attached, the least stable it is. You can form this pretty easily. You cannot form that all that well. It's very hard to do, all right, if not impossible. Okay. Finally, what is the relationship between these two compounds?
Are they? Wait. Is it? I forgot how to. I don't know how to pronounce it. Diastereomer.
Diastereomers. Yep, because they're not mirror images of each other. Diastereomer.
Diastereomers.
Mm-hmm. Because they're not mirror images. What would be the easiest way to check that if you were unsure?
Honestly, the way I just thought about it is that, like, I looked at them and they were the same, but the only thing that I noticed is that, like, the first, like the one that was like this was flipped, and I've just kind of associated, like,
figure out what the stereocenters are. So I'm going to give you guys a couple minutes to figure out what those stereocenters are. All right. So you have two stereocenters there. Figure out what they are. So if you figure out what they are, you can figure out what the relationship is. So I'll give you guys a couple minutes. I need to grab a drink of water or something. I know this is tedious, but this is the easiest way to double check it. This is something that if you have time at the end of the exam, when it's like this type of question you do, if you don't, then do your best guess. All by myself. I don't want to be all by myself. So you are going to be S. Wait, no. Yep, 1, 2, 3. You are going to be R. So then you are R. And so SR and RR. So this should be diastereomers. Just to double check, is that what she got for this one on the answer key? Just to make sure we're all on the same.
answer key. Oh, it says enantiomers.
Really? Are you looking at the correct answer key?
Yeah.
Hmm.
Okay. I don't know. Numbering around it.
Mm-hmm.
I don't know. I don't see how I can, like, try to show it.
That's fine. I would go by her answer keys. This doesn't look like that to me, but trust her answer. So, but
Okay.
this is the easiest way to figure out if something's an enantiomer or a diastereomer.
Is this 11?
11E.
Yeah.
Yeah.
Okay. Yeah. She's put a note in it. It's an 11E. Left compound should be S then R, and they're
Diastereomers.
Yeah, diastereomers.
I am the greatest man alive. King Kong ain't got shit on me. I was worried there for a second. Yeah, so we figured out the stereocenters, right? This is SR, and then this is RR, right? So do my stereocenters flip? Do I go from, this one flips, right? I go from S to R.
Yeah.
But this one stays the same. So if they don't both flip, but at least one changes, then it has to be a diastereomer. Does that make sense? Are you okay with that?
Yeah.
if the other one ended up being RS, then that would be the enantiomer. Makes sense. Maybe yes, maybe no.
Just to make sure, like the carbon with like the 4 groups attached to it would be like right here, right?
Mm-hmm.
Okay, I just wanted to make that.
Yep.
I low-key thought it was like the methyl groups, just because like they were attached to like 4
Don't
different.
forget, methyl groups can't be stereocenters because you got to have 4 different things attached.
Okay, thank you.
Yep. How's it going, Matthew?
I think I'm remembering distereomers now.
Okay.
I didn't remember earlier, but now I do.
That's fine, as long as it's all in there. So I think that's it for this practice exam. So on Saturday, I think I might host something to do practice stereocenters and stuff like that, or stereochemistry or chair flips. There's a lot of things I know you guys need help on because you have an exam next Friday. So I was thinking Saturday, Tuesday, and Thursday doing stuff for like review problems and whatnot. So all right. And if nothing else, you can always just check these videos out on right there on the YouTubes. So
Would it be like at the same time?
yeah, I think we said we're gonna do around the same time.
Okay.